much for joining us today to our webinar seminar series. And today with Professor Randall Davis. He's going to be presenting on one of those very interesting research work he's been doing, titled Diagnosing Neuropreventive Health via Subtle Science Signals in Behavior. And we're going to have, that's the first half an hour. You know how this is working. The second half an hour, we'll have Dr. Penny, who is our Professor Davis' clinical collaborator. And yeah, we're ready to go. Thanks very much.
Actually, the way it's going to work is that I'll be presenting the work largely. Dana's out there in Zoom land with her mic at the ready. So when I make a mistake, she will jump in to correct me and or augment what we're talking about. Speaking of jumping in, I'd much rather have a conversation with you folks than just stand here and lecture. So if anything comes up, anything confuses you, please feel free to jump in and talk about it. We're running a little late because one day the ultimate AI success will be setting up an AV system on Zoom without a problem. The hell with the Turing test. This is the Zoom test. Okay, so that's me. Dr. Dana Penny is my co-PI in this work. We're two halves of the team. I'm the technical half, unsurprisingly. She's the director of neuropsychology at Beth Israel Leahy Health, and we have been working together as a team for quite some time. There, okay. We're going to start off by telling you a little bit about some of the early work we did on something we call ECT Clock, because that's a mature piece of work that we produced, and I think it has some interesting results. That will also give me a chance to introduce some of the key elements of our approach, which include capturing natural behavior, the way people actually behave in ordinary life, not necessarily in specific testing circumstances, and an interesting idea called using the subject as their own control. This is an interesting and I think powerful idea. I wish I could say we thought of it. It actually comes from one of the first tests that I'll tell you about. What we have been able to do is leverage that in a number of interesting ways. Then I'll spend most of our time talking about the current research that we're doing. This current research is much newer than some of the other things that have been presented in the seminar series. So we're got some interesting and provocative early results, but not the kind of well-established definitive results that you've probably heard of in some other seminars here. We'll talk a little bit about the potential impact of the work. Part of the idea is to capture behavior just once and analyze it from multiple different perspectives. We're starting to work on a framework for interactive remote testing. And by and large, the aim of our work is to enable the preclinical diagnosis of neurocognitive disorders. That is, all right, that's what we're after, and you'll see that that's a theme throughout much of the work. Okay, let me motivate this. People talk in terms of a tsunami, which is heading our way. The good news is, in the past 30 years, medicine has made an enormous amount of progress against heart disease, strokes, a variety of things, cancer, that have resulted in mortality worldwide. So the good news is we push back on a lot of those diseases. The bad news, such as it is that people are now living long enough worldwide to become susceptible to the diseases of late age, namely things like dementia. And there is, in fact, literally a worldwide problem here. According to statistics back from 2018, there are about 50 million cases of dementia around the world. It's estimated that $800 billion is spent in the direct care of those people. That's the direct care, like the hospital and the doctors, not all of their family and other folks who help to care for them, which is not actually accounted for here. By 2030, the estimate is there will be 2 million cases costing $2 trillion a year, yes, with a T. And by 2050, perhaps 150 million cases. I don't even want to do the arithmetic of extrapolation for something like that. There is an enormous economic problem. There's an enormous social problem. How do we deal with 150 million people who cannot care for themselves? There will be a social strain and economic strain. It's quite a problem. Now, what we would like to do is to be able to diagnose the earliest versions of these kinds of conditions. So we want to do that as soon as possible, because while there aren't cures for these diseases, there are ways to control the speed of development of the disease. And some of those things are not medical at all. Some of them are just simple good health hygiene, exercise, diet, and so forth. There are no pills yet, but there are things you can do to slow down progress. That's why we want to start working with that, why we haven't worked. Okay, let me take you back to the beginning of our work. There's a classic test called the clock drawing test that has been around for literally 50 years. It's surprisingly simple. The doctor hands you a sheet of paper and a pen and says, please draw a clock showing 10 minutes after 11. You draw it. I take away that sheet, hand you another one, and say, please copy this clock, which not incidentally shows 10 minutes after 11. Now, as simple as this test is, it's quite revealing, because if you think about it, you're using different cognitive capabilities. On the blank sheet of paper, you have to think about what a test is. You have to understand the language like 10 minutes after 11. You have to think about where hands go in setting up a clock. There's a cognitive load to that. If I say, please copy this, all you have to do is copy. Cognitive load is much diminished. So the other interesting thing about this is you're doing the same thing twice. The same thing. You draw the clock according to instructions, then you draw the clock by copying it. We've asked you to do the same thing under different cognitive loads. That's very clever. That's what gives us using someone as their own control. Because if you just naturally draw slow, then even on this copy, you're going to draw slow. If you draw quickly, you're going to draw quickly here as well. So it's the comparison between the unloaded and the cognitively loaded version of the task that gives information about your cognitive state. Everybody's a little slower doing the one that takes some thinking. It's the difference between that and the unloaded one that tells us something about your cognitive health. We've been doing this for literally 16 years. We started back in 2005, initially at Leahy, where Dr. Penny is. Subsequently, expanded out to the Framingham Heart Study, Mass General Brigham. We have colleagues at the University of Florida in Gainesville and several other places who have been using this technology. This technology, by the way, is this device. It's a digitizing ballpoint pen. It looks and feels in your hand like an ordinary ballpoint, but it can decide where it is on the printed page because there's a very faint dot pattern that gets printed on the page. And the firmware in the pen has a camera in it to decide where it is on the page. And interestingly, it can figure out where it is to within a fraction of a millimeter, 75 times a second. Now, some of you are thinking, why not just use electronic stylus? Think of the audience we are asking to do this. Imagine handing an iPad to somebody who's in their 80s. Okay? Unfamiliar, we want natural behavior. Nobody who we handed this pen to ever said, I'm no good with ballpoints. Okay? It's a perfectly reasonable task that we use it. Now, importantly, we're not just collecting the electronic ink here. That's the easy part. What we really want to do is rethink the task and rethink the analysis. One of the ways that you'll see that we're rethinking the task is by measuring things that aren't ordinarily available. For instance, almost everybody pauses between drawing the numbers and placing the hands when you ask them to set the clock time. It's just natural, you have to stop for a minute. But people who are impaired pause longer. You know how much longer? Fractions of a second long. But because every point that the pen measures is time-stamped, we know exactly when different pen strokes happen. And that gives us a great deal of information that we can put into good use. And I'll talk a little later about the fact that we have, in fact, begun to do this on a tablet platform. Now, this test was developed over many years with lots of assistance with colleagues in various places. And it's currently, we saw it through to FDA approval. It's been licensed to a startup company. It's being used in Alzheimer's and Parkinson's disease pharmaceutical trials in various places around the world. It's also been fairly successful in terms of awards that it got. The Society for Operations Research and Management Science gave it its 2016 Innovative Applications Award. I'm particularly proud of that one because we went up against IBM in the finals, and our 5-person team beat IBM. MIT Solve as a contest yearly, and we were one of the winners in the brain health category in 2017. There's a fascinating organization on the West Coast called Not Impossible that tries to find interesting technology for human applications. And in 2021, our colleagues at Harvard Aging Brain Project published a paper in Neurology with class 2 evidence that an implementation of our tool outperformed the more time-consuming neuropsychological tests. And importantly, it correlated well with Alzheimer's, amyloid, and tau imaging biomarkers in clinically normal adults. How many people know about amyloid and tau? Okay, a scattered of people. These are the kind of nasty things that show up on brain scans in people who are having problems with Alzheimer's disease. Their exact role is still not well understood, but you know how you find out about that? You inject people with various kinds of dyes and you run them through a scanner. It's thousands of dollars, takes a long time, and is amazingly expensive. We're talking about something that takes 4 minutes, is a pen on paper, and gives some of the same information. That's remarkable. And we built up a large collection of data and published a paper in machine learning 7 years back, where along the bottom axis, you can see the names of a whole bunch of different models we built. And on the y-axis, you can see their performance in terms of AUC, the area under the curve, which of course we can just take as a measure of accuracy. On the far right, we have an indication of what happens when humans do this by hand. And if you look at what's been reported in the literature, when those things are studied retrospectively, their accuracy, their AUC, is somewhere between 0.6 and 0.8. When we built our best machine learning model, its accuracy was around 0.9, which, as you can see, far outpaces human performance. And we had the usual good news. It's really good performance. We also have the usual not so good news. It's a black box. We have no idea why it's doing what it's doing, and the way we make it better is by trying to train it with some more examples. So we took a purposeful middle step and built a model that's called SLIM, which is super sparse linear integrated model, linear integer model. This is work we did with blocking on her name. Damn. All right. Cynthia Rudin, thank you. Cynthia Rudin, who was here at MIT and is now at Duke. And you may have heard Cynthia's name recently because she's the second winner of the $1 million prize for applications of AI to humanity. Now, I won't say it's just because she did this. It's a joke. She had a long career doing these kinds of applications. I'm sure this can help, and we're impressed. Now, one of the things we got from developing and using these tests over the years is to suggest several guidelines for developing these kinds of clinical tests. First, they ought to be grounded in existing practice. That's how you get things accepted. If they're completely novel, it's much more difficult. We want to redesign them to take advantage of the new technology, but we want to be not tied to a specific device. You'll see that in the case of the pen in a few minutes. We want them to be quick. It ought to take about 2 minutes for somebody who's healthy. In order to cover multiple cognitive domains, memory, planning, learning. There's all sorts of different aspects to cognitive health. We'd like it to be culture neutral and language independent. Luckily, clocks are pretty universal around the world. That's one example of culture neutral and language independent. We ought to cover the lifespan if possible. That is good for young children right up to nonagenarians. And importantly, we want to use that idea we showed you earlier, using the subject as their own control, make it interactive because that gives us interesting indications of people's behavior. As I said a few moments ago, we want to capture novel behavior. We want to capture natural behavior. Okay, so that's some background about what we did with the clock test. Now let me tell you about a new test that we've been developing and trying out. We call it the digital maze test. Yes, ma'am.
So how sensitive is this test? No, sorry. How sensitive is this test? Like, let's say if you're thinking about clinical trial, maybe they try to find the right amount of drug. So you shouldn't just say, you know, impaired or not, it should have the gradation. Does this?
Yes.
Implement?
The FDA approved version in use in clinical settings gives you an answer on a scale from 0 to 100. And 75 and above is considered normal within normal limits. 50 to 75 is indeterminate, we're not really sure, and below 50 is regarded as impaired. So it does have a fairly detailed scope. I don't have a precise sensitivity figure for you, I'd have to go look that up, but we understand very well that it can't just be yes or no. Okay, mazes have a long history in psychological testing. You even took some in grammar school. Traditionally, the maze test is, here's a maze, find your way through it. If you solve that one, here's another one, which perhaps unbeknownst to you is harder. And they just keep stacking them up until you run out of time or they run out of mazes. We want to do something a little bit different. Here's a maze. Let me ask you to take a moment and try and solve it with your eyes. Notice anything interesting about this maze? No is not a good answer.
It's completely deterministic.
Completely deterministic. Another way to say it, said by a probability specialist, of course. There's only one path. There's no choices. Here's the answer. Okay. It's called unicursal in maze nerd speak. That's their term, meaning there's only one path through it and there are no choices. So we started off with a maze like this, not this exact one, but a maze like this, and thought, what if we were to select certain walls and get rid of them? If we do that judiciously, we can create another maze that has the same solution, but that also has choice points. Now, why do I want another maze paired with the first one that has the same solution, but has choice points? It's really a question for the audience. I want to see if you're with me. Louder. It's a control for yourself again, she said. Exactly right. Because once again, we're asking you to do the identical physical task under conditions of different cognitive load. And it's not the absolute speed with which you get through the test, it's the relative speed of the no choice followed by the choice maze. So our testing paradigm is no choices followed by choice maze. And by the way, no one has ever said, oh, this is the same maze. They don't get enough time to look at it. And they don't know how sneaky psychologists can be, so they don't guess. So we go from choices to no choices. It's the same solution. So as I said, it's the same graphomotor demand under a different cognitive load. Higher cognitive load means we get slightly different behavior, decision making. That allows us to use the subject as their own control. And this is not going to show up on the slide, but it also allows us, importantly, to calibrate and separate the motor and cognitive components of impairment. Some people, there is a physical impairment, but not a cognitive. In others, it's just the other way around. In some cases, you have both. And this testing, where we have both at the same task twice, allows us to separate out motor and cognitive components of impairment. Here's a maze, an example of a maze. This is a screen capture. The solution is indicated there, and of course on the form itself, it isn't really. But all we're going to do here is play back the data that's collected by the digital pen. Now watch when they get to decision point. Should I go up or straight? Now I'll go straight. This one's harder. What if I go up? No, left, right. Okay, I know what to do. And we continue on. This is being played back in real time. Again, since we have time-stamped data points, we know exactly when they got where. And if we were to wait through, we'd see that the subject solves the maze. A traditional maze setup, the answer is they got it right. We know more than that. because we know exactly where the pen was from moment to moment. So we can color code it, where green means that's going at the average speed that this subject used on that maze. Yellow means they slowed down a little. Red means they slowed down and perhaps stopped. And we believe that the patterns of slowing down and the patterns of stopping are indicative as well about cognitive health. Now, we did some analysis of these mazes, and one of the things we looked at was total completion time. How long does it take you to get from one end to the other? We did that across people who are HC healthy controls, AMCI, MCI is mild cognitive impairment, and AD, full-blown Alzheimer's disease. We looked at the no choice performance, we looked at the choice performance, and unfortunately, we got no significant difference between healthy controls and AMCI in either case, and maybe an ability to distinguish the two higher categories against AD. But that's kind of a no-brainer because people with full-fledged Alzheimer's disease are reasonably easy to spot. So we did something else. We looked at the difference in completion time on the choice versus no choice. Once again, looking at the task with a lower cognitive load and a higher cognitive load. And the difference in time turns out to be quite informative. We can separate mild cognitive impairment from Alzheimer's disease rather effectively, and the healthy controls from AMCI. These are important because categorizing patients with AMCI is difficult. They look kind of normal and they look kind of impaired. To the extent we can actually catch them, these are people who are particularly good candidates for early therapy, early kinds of steps to slow down the progress of the disease. Now I'm going to introduce a little bit of obscure terminology, which, to be perfectly honest, we invented rather recently and is not as good as it could be, but you'll see why we need it. Here's one of our mazes. Here's one of the tiles in the maze. We think of these mazes as built up of these little squares. And if you see, that's where you start, go from bottom to top. And when you get to that square, that tile, you can go left, right, or up, okay? Not surprisingly, because you have a choice there, we call that a choice tile, in technical term. Here's another choice tile. It's on the solution path, and you can go, assuming you come down from the left, come up from the left, you can go up or right. So that's a choice tile. But look at this tile. That's one that's not on the solution path. If you make a mistake and go up that way, okay, you encounter another choice. And even though you're off the solution path, you're faced with another choice. We call that an embedded choice. It's embedded on the incorrect path. Okay, stick with me, we're almost there. If I look at this tile, that's a choice tile. It has an embedded choice on the non-solution path. So we call that a choice tile with an embedded choice. Interestingly, that's a choice tile without an embedded choice. And you can probably see where we're going with this. Question is, the embedded choices slow people down because they're sitting there trying to figure out which way to go. They may have extra choices to make as they look down the wrong path. I'll show you the results in a moment, but you need to know that we developed 3 different levels of these mazes. The easy one has, these differ in several properties, but the easy one has no embedded choices. The intermediate one has some. And the advanced maze has half of its tiles as embedded choices. If you look at the data here, if we look at the data, I know the numbers are too small to read, but it turns out that the average speed in the choice tiles does not distinguish between the groups at all. So I just take the speed in the choice tiles, that doesn't tell me much. It doesn't matter whether they're embedded or not embedded. If I mix those two together, I get no diagnostic. If I look at the average relative speed, that is somebody's speed compared to their own mean speed, and I look at embedded choice tiles versus non-embedded choice tiles. Turns out, once again, we can differentiate healthy controls from MCI, MCI from AD. Here's the data to back that up. Again, it's a little small to read, but we've been through this analysis. And interestingly, this information about people's behavior at choice points turns out to be revealing. And another interesting angle here, we're using somebody as their own control when we switch from the no choice to the choice phase. Here we're getting somebody as their own control within a test, because we're looking at their behavior on the non-embedded choices versus the embedded choices. So we're testing them, we're calibrating them within the single test, and this gives us extra stability. So even if people are tired because it's been a long day, this kind of test is likely to give more stable and reliable results. Now, if we look at the relative speed at embedded choice tiles, one of the interesting things in this data is that all of the clinical groups are higher than the healthy controls, the blue line at the bottom. The other thing you may notice there is that in the clinical group, their speed is almost always above normal, above average. It sounds like Camp Wobegon, right? Where everybody's above average. Turns out remember, this is just the speed at the decision points. So what this is telling us is they're zipping through the decision points and then slowing down in between. Question?
So the people that
That's down.
the people that you're testing against that are not in the healthy control, those people that are already pre-diagnosed, correct? So in terms of early detection, don't you have like the problem sort of like a distributional shift here where because people that you're testing over, because they've already been diagnosed, maybe it's already like pretty obvious that they have this particular condition, whereas like people that you aim to test on haven't been tested yet, and so it might be less obvious.
Okay, let me repeat the question. This is supervised testing, so we're using people who have already been diagnosed. And the question is, I think the classic one of any kind of machine learning. If I give you examples that are labeled and you do well on the training set, how well are you going to do outside of that, right? Is that the question?
But I think to some degree, but even like if you were to separate in a test set where the distribution of the test set is similar, so if the distribution of the test set and the training set in this case is the same, then it's okay. But what I'm wondering is if once you implement this and you actually use it clinically, if the distribution of the people that you're going to run it on is actually different because they haven't been diagnosed yet.
Yes. The distribution is asking whether they out in the real world, and that's what I meant. Once your classic question about machine learning is, it's great to do something well on the training set and the internal testing set. Right. What happens in the outside world? And that's a question for any kind of machine learning. Notice it doesn't matter, I don't think, what the percentage of each classification is in the outside world, because what's learned here is a set of behavioral properties where the behavior is how you move, okay? And we believe that is attached to the cognitive impairment. It's not a probabilistic notion of how often this thing is going to show up in people. It's how do your hands move in very subtle ways, okay? Now, the real answer can only be told in hindsight with lots of testing, but this thing has been tested out in the real world. It seems to be doing well. Okay, sorry, got ahead of myself. So what's interesting here, part of what's interesting is that if you look at item number 2 on the x-axis, the normal folks are rather low and the impaired folks are all much higher than that. This gives us some indication of how people behave on the test. As I was saying before, we suspect what's going on is the impaired folks are racing through. In particular, perhaps what's happening is they're starting out with the no choice test and saying, oh yeah, okay, I'm just going to go through this. And then when the choice test comes along, they say, oh, uh-oh, okay. And they may be zipping through the choices before they realize that it's harder this time around. So they're slower to recognize that. That's a hypothesis. We've yet to test that out. Now, there's an awful lot of information in these mazes. We have just begun to do some interesting measurements on them, as I've been suggesting. I'll let you just read that list. There's lots of things we can look at. The next thing we have done is eye tracking. We have an eye tracker from Argus Science, which is a Massachusetts company. It's wearable, so that it's not as awkward as some of the eye trackers. There's a little device you put in your pocket or on the table. You put on that thing that looks like an eyeglass frame. The shield, by the way, is a UV shield for using outdoors. It actually doesn't have to be used indoors, so the thing is even less intrusive than it might look at first glance. As with most eye trackers, the pieces that go under your eye have cameras in them. They look into your eyes to spot where your pupils are. And the thing on the nose piece is a scene camera. So it's looking at what you're looking at, and the eye cameras are looking at where your eyes are pointed. And between those two, you can tell where in the field of view you're looking from moment to moment. And it measures at about 120 measurements per second, so it's quite useful. Here's an example of one of our students doing one of the mazes. The green dot is where the system thinks you're looking at the moment, and he's using the digital pen, of course, in this case. And I want you to watch the relative location of the green dot and the pen. See how his eyes jump ahead occasionally? You guys have heard it, look ahead, right? Here it is literally. Now watch what happens at the upper left corner. Even though he's done this before, watch his eyes. He starts to dart around. He made a mistake. And even before he stopped drawing, his eyes gave away the fact that he knew he had made a mistake. So the pen tells us what you're doing. The eyes tell us something about what you're thinking about. And that's really intriguing. Okay, I know I'm racing through this stuff, but let me tell you about one more test we developed. It's called the single digit test. There have been single digit tests before. This is our version of the digital single digit test. Basic idea is you have both a key and a task. So left-hand side, there's a pairing of simple geometric figures and numbers, and then the test itself is those same figures, and your job is to write in the numbers. It's a single sheet of paper, or the only thing you can see is the key and that test. The second version of the test, we call the digit test. This is very difficult. There's the key at the top. There's the test at the bottom. And all you get to do is write down the numbers. Why do we want people just to write down the numbers? What kind of brainless task is that? We're not that dumb. Must be a good reason.
So the numbers in the key is the same as the numbers in the value? Oh, sorry. So the numbers in the key is the same as the numbers in the value, or it can be different?
The answer, you're on the right track. The answers in both the translate task and the copy task are the same. What does that allow me to do?
Like also doing some self-control, like
Use the subject as their own control. You see, we keep coming back to this idea. It's terribly powerful. If you draw slow, that's okay. We find that out of the copy task. And what you do on the translate task, by comparison, tells us the difference. There is also on this, in the way of sneaky psychologists are always doing, something called a delayed recall. After you've done the translate, after you've done the copy, then suddenly part of the test, a small set of 6 symbols like the translate task shows up, except the key is no longer visible. And what the subject says is, where's the key? And the answer is, do the best you can. And I say, but I don't remember. And the answer is, please do the best you can. Because they didn't know this was going to be a memory test. And what we're finding out is what they learned without even trying. Incidental learning. Okay? Yes?
Does it matter what, like in what sequence, like what order you do?
Does it matter what order they fill them in? Yes, one question we sometimes get is, what if you get a smartass who looks at the circle and the one and just looks for all the circles and fills in all the ones, right? We don't let them do that. The instructions are explicitly fill these things in order. If you start skipping around, you get urged not to do that. Did I answer your question? Okay. All right, so there's also the delayed recall. Test is also given twice in a row because the first time they don't know that there's going to be a delayed recall. The second time they do know because they're told this is the same test. We want you to do it again. We don't explicitly say, and remember there was a delayed recall here, just this is the same test. Part of what's interesting is to see if people learn from taking it the first time and do better the second time. Again, comparing them to themselves. Now, there's a traditional version of this test, which mostly measures information processing speed. By setting the test up the way we have, we get a lot more information out of it, in particular, we get processing speed at multiple different load levels. And in particular, the second administration, people think of the test differently. From thinking, I've got to go through this quickly, to I've got to go through this carefully so I remember, it changes how they take it. Those changes are interesting. Now, this repeat testing, I've said it enables measuring both incidental memory and applied learning. It also gives us a way of generating multiple versions of the test, which to the neuropsychological folks is important because you want multiple versions of the test so that you don't run out of the ability to give novel tests to perhaps new audience. Now, if we look at that delayed recall performance in particular, this is some data from Mass General, their aging brain study. These are mostly normal folks. They're senior citizens, but mostly cognitively normal. And if you look at the confusion matrix on the first trial of the single digit test on the delayed recall, that's what you get. People get a fair number. On the second trial, notice how their answers are much more often correct on the delayed recall. They have begun to learn about the test and they recall more. Okay, one of the things we wanted to do, or want to do, is score a single digit test automatically. Now that's easy because all we have to do is recognize handwritten digits, right? That's a well-known solved problem. If you look online, there are digit recognizers that will give you a 99.9% accuracy. Let me tell you about some of the problems we have. In fact, we use double digit numbers. We use 0, 1, 2, and 10, 11, 12 for business and 2. We have subjects who are impaired. We have people who overlap. We have people who cross out. In fact, here's an example of a delayed recall response that we got. Show me your favorite 99% digit recognizer and have it work on that. Okay. Here's another example. So there are people crossing out, there are people who are impaired enough to do strange things. So we want to do the best we can, even though we have a larger set of digits. And our response was, first of all, to extend the traditional deep neural net from 0 to 9 to 0 to 12 by the usual fashion of having lots of examples. Luckily, we have lots of examples of this test. So we have lots of instances of people writing down these numbers. We also introduced the scribble category, that is for things like, the second box in the top row there, I can't make much sense of. And even Kim, who's sitting here in the audience, is a master's student working on this stuff, is doing some very interesting work on trying to develop the best digit recognizer we can under circumstances where people are scribbling, drawing on top of things, and drawing things that are outside the expected set of answers. In an early test of this, I won't spend much time on this slide, except to say in the early test of this, it did a good job on comparing Alzheimer's and MCI against healthy controls with a AUC of 89 and distinguishing from healthy patients with AUC of 98. So we're classifying Alzheimer's and MCI against normal people, healthy people. And the right-hand curve in particular, that's a linear regression comparing healthy versus AD and MCI. It's basically a screening test. So it answers the question, how accurately can it pick out the people who appear to be impaired? And it seemed to be quite good. Okay, last thing I want to tell you about. Single digit, I want to talk about eye tracking in the context of the single digit test. What we expected initially when people are going to take the test is they might do something like this. You look at the symbol, you look up in the key, and you write down the answer. Look at the symbol, you look at the key, you write down the answer. But what might you do if you eventually have memorized the association? What do you think?
I just look at previous one. Okay.
You're a step ahead of me, but it's a good guess. We thought the thing you would do is just write it down because you don't have to look in the key. If you don't have to look in the key, you'll probably respond faster. The time from finishing up writing your previous response to writing this one will probably be faster. We spent a lot of time looking for that, but we couldn't find faster speed. The data was just too noisy to find a difference in the speeds. So instead, we started looking at their eyes. As a consequence, in a way that I'll show you in a moment, we've been able to detect learning in real time. We can detect when somebody makes the association as soon as they do it. We also found a range of interesting learning and test-taking strategies that are otherwise invisible. Standard strategy, look at the stimulus, go find it in the key. We also found, as this gentleman was saying a moment ago, that you might look at a previous instance of a stimulus that's already filled in. There are scanning strategies. Okay. Let me show you a video, and this is slowed way down. Even so, you have to watch carefully. The first 6 examples are a sample just to make sure the subject understands the test. And watch where their eyes are as they're going to fill in the boxes here. First one is it's the sort of plus, the fat plus sign. Writes down, sees it, writes down the 1, looks at the square, goes and looks for the square, starts to write a 2, makes a mistake, and then said, no, that's a 1, I add a square. The star, that's an 11. The diamond, where is it? There it is, 12. Okay. The rectangle, that's a 2. Didn't have to look. Triangle, that's a 10. The star, didn't have to look. The triangle, do you see what they did with the triangle? They looked back at the previous triangle. Okay. So there are all sorts of interesting test-taking strategies which we can capture by seeing where you're looking. It's enormously revealing. And what we've begun to do is build up a library of these kinds of strategies to see what people do and how they learn. And importantly, will that change with cognitive impairment? Alzheimer's disease is typically thought of as a disease affecting memory. We hypothesize that even before it affects your memory, it might affect your learning capability. So if we can capture the learning association as soon as it happens, and capture the loss of that association, because if later in the test you have to go back and look up that symbol, we know you've forgotten that association. To the extent we can figure out what you've got, how long you had it, and when you lose it, that might be a particularly early indication of cognitive impairment. That would be amazing. And here's a graph of how long people spent looking for the symbol when they were scanning the key. The blue is the first time through, and the orange is the second time through. As you can see, they're quite clearly going faster. Learn something? Yes.
I thought something that was quite interesting in the previous slide is that the person who learned without looking at the key to fill in the rectangle actually had learned 2 things, had learned 2 things at once. When he misclassified the square as a rectangle, both knew how to classify the square correctly and also the rectangle because he had a mistake on that particular instance.
Hang on 1 second. Having been on the audience in many of these talks, I've gotten incredibly frustrated with not hearing what people are saying. Wait 1 second, I'm just going to repeat that part. He noticed in the movie that it seemed like the guy who was taking the test learned 2 things at once. When he went back to double check, the difference between the rectangle and the square, it might be that he picked up the association of both of those.
So my follow-up question is, in terms of like the test that you apply, did you test any differences in terms of if a particular key has multiple shapes that are very similar to each other versus multiple shapes that are very distinct, in the sense that those kind of conflicts may occur more often or less often?
Okay, very good question. What does the relative homogeneity or inhomogeneity of the shapes matter? We don't know. It's a good question. We'd have to do much more testing. There is some possibility that the degree of pointiness of the shapes may have an influence. The stars, the triangle, the diamond versus the squares, the rectangle, the circle. But we don't know yet. But that's exactly the right intuition one ought to have, particularly for psychological tests. You have to constantly think, what else might they be paying attention to other than what I thought they would be paying attention to? So the question's very good. This is a quick screen capture from an iPad version of this test. And one of the interesting things of the maze test, one of the interesting things we wanted to explore here is to what extent can we make the maze test self-administering? So we can hand out the iPad and people can take the test on their own. So one of the things you want to be able to do is have the iPad offer the same sort of gentle corrections that human test administrators do if you start to do something funny. So let's see what happens here. And this is just, again, a student doing the test and then purposely making a mistake.
Please don't go through walls.
I don't know if you heard that, but on my speaker it said, please don't go through walls. The iPad speaks up. So when it detects you've run through a wall, it stops tracking your pen, shrinks down your field of view and says, start over again and continue. Or start again from where you finished. This is, I think, going to make it possible to have these tests be taken independently. We're basically looking at ways to make the iPad a test administrator in the same way that people administer the test. Okay, finally, another device we've been working with is a company called Multimodal Health. These are things about the size of a watch which to your wrists and ankles. And it turns out that if you have something like Parkinson's disease, which has one of its symptoms, uncontrolled motor movements, which get progressively worse, if you put these on and adjust the frequency and intensity of the vibrations, it can make an enormous difference in the degree of tremor that you have. It's really quite remarkable. Here is a movie. This is somebody wearing an early prototype. You see the white box on our upper right arm? That thing is going to be turned on. At the moment, you see it says before it's turned on, she's going to be struggling to write. Again, this goes by quickly. Once it gets turned on, watch what happens. This is her normal, at the moment, unfortunately, her normal way of trying to move. Once it's turned on, look at what happens. She can write her name, she can write things, make straight lines. Those are her parents sitting next to her and crying, saying, oh my goodness. Okay. It's a remarkable phenomenon. Now, knowledge about this has been around for a little while. That's why Multimodal Health is interested in making these things. The interesting thing here, near term, is for reasons people don't entirely understand. These things reduce tremor. And by the way, the devices are both vibrators and sensors. They measure the orientation and acceleration of your wrists and ankles. So it not only tries to vibrate to inhibit motion, but it knows exactly what your motions are doing. And in Bluetooth, we can download the data. Again, it's 100 measurements per second, so it's quite detailed data. The really interesting speculation is that in one of these events, at least one subject said that when the vibration was on, it seemed to them they could think more clearly. That's remarkable. Could it be that by inhibiting tremors, we enable neurocognitive improvement, not just physical improvement? Maybe when your brain isn't so wrapped up in in trying to battle against involuntary movements, that you think better. Wouldn't that be remarkable?
How does this compare to like the treatment, like the drug?
How does this, the question is, how does this compare to treatments like drugs? First of all, it's not a drug. It doesn't have to be taken, injected, or wherever. And there is several years worth of experience, not a decade, but several years worth of experience with this stuff. And as far as I know, take it with a grain of salt, there are no bad side effects from this. The mechanism is not entirely understood. People have speculated that it may be some sort of interference with a feedback mechanism. You know, your muscle starts to move and you want to correct it, you overcorrect it, and you get into this kind of thing. Maybe this vibrating interrupts that, not entirely. I'm going to take 1 minute to tell you a really interesting story of synergy. Where did this technology come from? Somebody wanted to make it possible for people who are deaf to dance to music. Now, if you're deaf and the bass is loud enough, you can hear that and you can move there. But they designed a vest that had a bunch more vibrators in it, not just for the bass notes, but for other notes. If you put on the vest, you could feel the music, much more detail. People were dancing with it. And the remarkable thing about that is when they tried this out on people with things like Parkinson's disease, they could move better. So they turned that technology into this. It's remarkable. Okay, let me finish up because we're about out of time. Luckily enough, here's my summary. Oh, sorry. Yes.
Have you demonstrated using the previous tests that you've shown to us, like base completion and others, and the performance changes when you put the devices?
The question was, have we demonstrated that the performance changes when we turn on these sensors? That's the research that we're doing. Okay, that's what we're interested in.
And are you also using it on healthy controls?
And are we also using it on healthy controls? You bet. Dr. Penny is a certified psychologist. She knows how to design these experiments so that they're reasonably tight.
Imagine to yourself in C-cell, in half of the students, this kind of devices, and then we can measure the impact of number of units submission. I think it's a fair experiment.
Yes, so yes, what she's saying is that the experiment design in C-cell is not necessarily that tight. And if I had designed the experiments, it probably wouldn't have been like that. But Dr. Penny is a stickler for good experimental design, so we did better than that. Okay, let me summarize. We try and capture the vial of behavior and then analyze it in various ways in conscious analogy to the vial of blood that they take from you and then run multiple tests on. The good news is our data doesn't go stale. The blood is only good for a certain amount of time. We have data from tests from patients we tested 15 years ago. And as our analytic techniques have gotten better, we can go back and reevaluate those tests with new measures. That's the advantage of digital data. We want to do that by natural interaction, giving people things that they do as naturally as we can. We're going to explore learning in real time. That's the idea that maybe learning capability decreases even before memory capability increases. We want to make this possible to do in remote areas independently because the problems are of global proportions. We think this will contribute to an understanding of cognition to the extent in particular that we understand about how movement and cognition interact in both directions. Does movement cause problems with cognition? And finally, we think it also gives a possible start to a new model of human-computer interaction, which I call inadvertent interaction. We all do things explicitly when interacting with computers, but when we interact with one another, there are all these other channels of information. The look on my face, how I tilt my head, the tone of my voice. Human-human interaction is extraordinarily rich because we're tuned into those channels. The computer isn't. It's very interesting to have human-computer interaction with those signals as well. With that I'm done. I'm happy to take more questions. Okay.
Hi, Randy. Can you hear me?
Yeah, if you take off your mask, I can hear you
I'm
better.
not going to take off my mask, but I can go. Can
Okay.
you hear me okay?
Yes.
Great. I'd love to use these types of eye tracking experiments within our research on HCI in electronic medical records. Can you tell us a bit about what the state of the art currently is for eye tracking and how feasible it is to deploy it at a massive scale?
To
Deploy it at a massive scale. For
Yes.
example, is there any way that we can use eye tracking as part of every doctor looking at electronic medical records?
as usual, the only question is, can you afford it? Okay, because the device that I showed you is $13,000. Maybe in a hospital, that's not too bad, but I can't see it on the Medicare charge sheet. More realistic answer. So in the short term, the answer is no. In the medium to longer term, one of the things we've been looking toward is the possibility, if you're working with an iPad, that the camera on the iPad may be usable for at least some degree of eye tracking that's good enough. It may not get moment to moment, but consider the simple digit test. All I really want to know is where you're looking within a reasonably broad target. So it's possible that if we can get eye tracking on the iPad to work accurately enough, then I think you do have something.
And if you have someone looking at a document,
Yeah.
do you think you can get it to the word level, the paragraph level, how detailed?
The reason I'm saying, the question is, if you have somebody looking at a document, can we get it to the word level, to the paragraph level? Okay, let me show you something annoying when people are looking at documents. Where am I looking? This is not a trick question. Where am I looking? Down, okay? The view of my eyes from down is much reduced from the view of my eyes from straight ahead. And almost all the eye tracking technology is for supermarkets. Where are people looking on the shelves? Okay, how does somebody watch a ping pong match? Okay, not very much of it is aimed at the ability to track people looking down. That's one of the problems we've had, and we've been struggling with it a little bit. We started out with a previous eye tracker, which we had hopes would work, but didn't, so we switched to this one. Maybe if we can convince people there's a market for it, we can actually get them to build one, because I don't think it's not terribly more difficult. It's just understanding that looking down is something you want to do. You don't want people having to do this, tilting their head perpendicular to the page.
I just wanted to add that a number of our computer vision faculty, like Antonia Toralba and Wojtek, they actually developed an eye tracker that uses camera and uses a multiple application. I don't know if it is refined enough for what it sounds like it's suggesting or you are using, but it may be worth checking because it is.
Say again? Oh, she said some of the computer vision folks have developed an eye tracking capability with cameras. Well, these eye trackers are using cameras.
We use the camera of your computer.
Yes, right. Now, so the question is, can you do it with, say, the webcam that's on my computer? And the answer is yes, that's actually been possible for a while. If the document is here on my screen, there's websites you can go to, and you can even play games using your eyes, okay? So that capability is there.
That's free.
What's that?
That can be free then.
Yes, that's free.
And how can it get to the word level, you think?
A while ago, it was not bad. Rough area of the screen. I suspect it gets better over time. I haven't tried that in a while, in part because that doesn't do us much good. We need something where people are, working on this. If you have people reading documents off the screen, well, there's actually a bunch of things that do it. If you have people reading documents on the screen, there are band-like sensors that sit at the bottom of the screen that you can attach. They're relatively inexpensive, and you calibrate them, and they have pretty good tracking on the screen. If you look over here, they won't see you, but if you're looking at the screen, I believe, offline, I can give you some names of people to look at, companies to look at. Yes, sir.
That's really interesting work, very exciting work, and the main application, if I understand well, is dementia. Have you considered different types of dementia, not Alzheimer's disease, but from the temporal dementia, vascular dementia?
Yes, I will abbreviate to make it easy, though my co-PI is more than welcome to jump in at this point. But yes, she is, of course, quite familiar with the whole spectrum of dimensions that are out there and how they differ. We also aren't necessarily limited to looking for diseases. There are a bunch of people whose job requires their capabilities to be periodically recertified. Airplane pilots, long-haul truck drivers, they are eye tested, but they're also cognitive tested. The ability to test the cognition of somebody like that could be a very interesting added capability. Then there's Medicare. Everybody over 65 is entitled to a cognitive assessment once a year. And it's not because we think they are dementing, but because it ought to be a standard screening test. So there's a large market there as well. So it's not just looking for diseases, it's calibrating cognitive status.
I guess my question is, do you have some indication that you can pinpoint different types of diseases, or is it like an overall measure of cognitive ability? So you don't have it very specific.
Let me say for a moment that I think we're still in the relatively crude classification stage, but Dr. Penny, do you want to step in and enlarge on that? He was asking whether we can be more refined than just say normal MCI and 80. No, I don't know. So I think you'll have to take my word for it for a moment that we're not that refined yet. That's an obvious, that didn't come up. That's an excellent next direction, which it'll take a bunch more work for obvious reasons. That's what I meant to say.
But we have, sorry, but we have data from this kind of patients over the 15 years.
Yes,
right?
what we don't have is enough. He said, do we have data from these kinds of patients? Yes, but at the moment, our numbers for things like MCI and various kinds of dementia are small enough. It's when we group them together that we get big enough numbers for these kinds of experiments. Yes, in time, we'd like to have data big enough for each of those subcategories as well, to be sure.
Any other questions? So thank you very much. Thank you.